All right, we're going to start here with Chapter 6, the normal distribution again. And we're doing Section 6.2 this time, which is an extension of 6.1. It's applications of the normal distribution. And so the objectives are pretty much these first five. We're going to talk about whether the distributions are symmetric or skewed. That allows us to know whether we can use the data or use these characteristics of a normal distribution to help us make decisions or find out information about data. We already know the properties. We've already gone over that. Finding area under the standard normal distribution given the z-values. Today we're going to have to find z-values. We'll be given the data numbers and we're going to have to find the corresponding z-values that go with those. Finding probabilities, which since the area under the curve is 1 or 100%, we can think of those areas as also probabilities. And then find specific data values for given percentages using this normal distribution. So let's go on forward. We can solve a lot of practical problems using, and a lot of data fits this normal distribution, which is what this is saying. And all the problems in this chapter, you can assume that the variable is normally or approximately normally distributed. And sometimes the problems even say, that the data is normally distributed. So let's go on. We're going to have to change numbers from the value that we get into z-scores or z-values. And once the variable's transformed, then it's just like we did with 6.1, where we go to the table and work our magic and find out what the area under the curve is and make some inferences from that. So let's work a few examples. These are examples from the text. This is 6.2, Section 6.2, Example 6.6, page 317. I hope talking through these and working through them helps you a little bit. So let's look at that one. This is summer spending. A survey found that women spend on average $146.21 on beauty products during the summer months. Assume the standard deviation is $29.44. And find the percentage of women who spend less than $160. So, if you're on your own, this next slide's going to have the curve drawn. But if you're on your own, you draw your own curve. So, draw a line. Draw a line. Okay, my lines are not so hot. So let's just clear that off. Okay. Try to draw a straight line this time. So we're going to draw a straight line. And we're going to draw a normal distribution here with one peak out in the middle. Our mean is going to be right down the middle. And the mean is 146.21. Okay, so there's our mean. Standard deviation is 29.44. That's going to be, of course, sigma in our formula. And we want the percentage of women who spend less than 160. Well, 160 is bigger than 146, so it's over here somewhere. May not know exactly, but we can place it on this curve. And we can draw a vertical line down to that. And we know that this is the part of the curve over here that we need for our answer. We want the ones that spend less than 160. So sketch it out yourself. That's what you're going to have to do when you have your homework. Now, the next slide has it all done for you, but you don't have that option. You're going to have to kind of do this little sketch on your own. So going to the next slide, you can see that it's much neater than the one I drew, but there it is, the normal distribution curve. What we have to do is we have to take this 160 and change it to a z-score, and for our mean of a normal distribution, it's at 0. And for the z-score will be 0 at the mean. So let's go on and see how to do that. This is a formula that you need to memorize right here. This formula right here is something that you need to memorize. The z-score is x minus mu over sigma. X is the value that we're looking for, or the $160. Okay, subtract the mean, which is 146.21, divided by the standard deviation, which is 29.44. And it gives us a z-score of 47. Okay, so what these were left over from the last slide, so let's get rid of those. Okay, so now we need to go in and look up in table E the area under the curve. So we're going to go and do that. Let's look under the area under the curve for table E. And let me go back because I forgot. 0.47. So we go up here to 0.4 and we go across. Again, we did this the other day. We go across and we look down here at 7, so that's 0.47, and that's where that number 0.68082 comes from. So you can do this with your finger. You obviously don't have to draw a line, but do that with your finger. And where those meet is the area under the curve. So we go back, and so it gives us an area of 0.6808 right here. That's that whole area, because remember the z-score measures less than, everything less than, which is what we were looking for. And so that's the area we're looking for. And we can change this to a percentage, multiply it by 100, because 100% of the data is under the curve. 68% of women spend less than $160 on beauty products in the summer months. All right, let's go on to the next problem. Page 317. Here's newspaper recycling. Each month, an American household generates an average of 28 pounds of newspaper for garbage. So here's our average right here in the middle. Again, if you're drawing it, you place that number there in the middle. Assume the standard deviation is 2 pounds, so this is our sigma right here. If a household is selected at random, find the probability generating between 27 and 31. So place these numbers on either side of the mean, or however they are related to the mean, depending on what they are. Place them on the graph, and then you know where you've got to find z-scores. Now, remember when we had two z-scores, it reads to the left. So this is going to give us the area to the left of 27. When we find the z-score for 31, it's going to give us that area. And so we're going to have to subtract them to find this area between. So we're going to look up, we've got 27 minus 28 over 2, x minus mu over sigma, and we get negative 0.5 for a z-score, that's this one. And then we get 1.5, 31 minus 28 over 2, for our z-score that's above 28. And so let's see, negative 0.5. So here's our negative. 0.5 would be right here. Whoop, no, that's wrong. 0.5 is right here. 0.50. So 0.30854. Okay. And then 1.5, positive 1.5 is right here. 0.93319. So we've read both the z-scores off the tables. And go back, and those are the numbers they got. They rounded to 4 decimal places instead of 5. Subtract the 2, like I said, because, you know, we've got to find this shaded area. And 0.6247 is our answer, so the probability, multiply that by 100, is 62%. That between 27 and 31 families recycle. We'll go to another example. This one's on page 319, example 6.8. Coffee consumption. Americans consume an average of 1.64 cups of coffee per day. So if I was to draw this out, I'd have this, and I'd draw my normal distribution. My mean is right here, 1.64. Okay. Cups of coffee a day. Assume the variable is approximately normally distributed, standard deviation. So this is my sigma right here. 500 individuals are selected. This puts a little different spin on it. We have 500 individuals are selected. Approximately how many will drink less than 1 cup per day? So we're down here below the mean at 1 cup. So we're looking less than 1 cup. So we're looking at this area over here for our data, for our problem. And so we get a z-score here. It's going to be negative because it's below the mean. So let's go calculate that. There's the distribution curve. We just drew our own. And 1 minus 1.64 divided by the standard deviation of 0.24 is negative 2.67. So negative 2.6 right here. Go across. Can't draw a straight line. 0.7 down here. 0.0038 because it rounds to 4 digits. We'll go back, and it is 0.0038. I just like to show you that so you know you get the verification. That is the area under the curve. So the probability, or the percent of people that drink less than 1 cup of coffee is very small. It is 0.38%. So if the question is what percentage of the people, or what's the probability of people drinking less than 1 cup of coffee, it's 0.38% of the people, less than 1%. But we need to know how many people that is from a sample size of 500. So we're going to have to multiply. We want 0.38% of 500, which means we're going to have 500 times 0.38%. And remember, when you're doing a percentage, you move the decimal place back 2 decimal places to the left. So we'll actually multiply by 0.0038, and that's going to give us the number of people, which says is 1.9 out of 500 that drink less than 1 cup of coffee. And we can't have 0.9 people, so we're going to round the answer to 2 people. So about 2 people will drink less than 1 cup of coffee a day. Our next example, 6.9 on page 320. This is another twist on this ton of problems. Now we know the percentage, and we have to find the z-score for that. To qualify for a police academy, candidates must score in the top 10% on a general abilities test. The test has a mean of 200, so we've got a curve here. We place the mean on it. The test and a standard deviation of 20, so there's our sigma right there. Find the lowest possible score. So we don't know a score. We've got to figure out a score to qualify. Assume the test scores are normally distributed. Well, we want this upper 10%. That means, remember, the z-score reads to the left, all this. So down here is 90%, or 0.9000. So that's the area under the curve that we've got to look for, is 0.9. So we're going to go to our table. Go back to a positive table. Let me find one. Okay, and find 0.9. As close to it as we can get. There's 0.89, 0.901. This 0.89973 is probably the closest to 0.9. So if we read over here to the left, it's 1.2, and read up 1.28, it looks like, is going to be our score that's going to give us an area of 0.9. So our z-score for that place is 1.28. So let's go back to that problem, and that's what they got. So it's 1.28 right here. Now, how did we get this formula? This is another formula that you need to memorize right here. This is how you find the x score. But say you forget the formula. Well, it's just algebraically solved from the z-score formula that we learned earlier. So let's go through and look at that. If we multiply both of these sides by sigma, okay, over here, sigma, which is sigma over 1, this cancels out to be 1. And so you have z sigma, z times sigma, equals x minus mu. Now I want to know how to get the score, so you add mu to both sides. Okay, so x is equal to mu plus z sigma. And that's the score that we just saw, but that's how you get it. So if you forget this formula, remember it. All you have to do is remember one, and then remember how to algebraically work through and solve for a different variable. Or you can remember both of the formulas. So let's go back. Here's the formula again that we're working with right here. Okay, so we have 200, which is our mean, plus 1.28, which was our z-score. So this is our mean, this is our z-score, our sigma was 20, and so our cutoff score is 225.6. That's the lowest score they can get, but we won't have a part of it. We won't have a 0.6 for a test score. It's going to be rounded, so you're going to round it up to 226. All right, this is example 610, page 321. Systolic blood pressure. For a medical study, a researcher wishes to select people in the middle 60% of a population based on blood pressure. The mean systolic blood pressure is 120, so they've put the mean on the curve. And the standard deviation is 8. Find the upper and lower readings. Well, if they want the middle 60%, since this curve is symmetric, that means that 30% are over on the right side here and 30% are on the left side. Okay, so half of a curve is 50%. That means there's 20% above this shaded area that we're looking for and 20% below the shaded area. So this area here is 0.2, okay, from this x that we're going to have to find the z-score for. But this one covers all of that to the left. So since there's just 20% above it, we're looking here for this whole area to the left, and that's going to be 0.8. Okay, because we want that whole area to the left of x1. So we're looking at for x2, 0.2, and for x1, 0.8, because all that's left above it is 20%. So let's go to 0.8 in the, here's the closest to 0.8, I think, which is when we read left and up, that's 0.84. Okay. And then we're going to go to 0.2, which is our negative one. So we go here and find 0.200, where we can find right here. Looks like this is our closest. And that's a negative 0.84. So, and that makes sense since they're symmetric that those scores would be the same. So we're going to go back and look, we have 0.84. So x is equal to the mean plus the z-score times the standard deviation. Okay, and that's 126.6. 0.72. That's this score. Okay. Then this one is 120. That's our mu. And if you wanted to say it's plus negative 0.8 because the z-score was negative. So the z-score times the sigma, and we get a score of 113.28. So 113.28 is our lower score. So the middle 60% of the readings are between 113 and 127. Okay. Now, a lot of distributions are not normally shaped, but there's a lot we can get from a normal distribution. And if they are normally distributed or approximately normally distributed, then we want to be able to use this information. So there's ways statisticians check for normality, and we're going to talk about 3 of those. The 3 we're going to talk about are histograms, Pearson's index or PI of skewness, and outliers. There's other tests called the normal quantile plot, chi-square goodness of fit, Kolmogorov, Smikarov test, Lilliefors test. We're not going to worry about those. We're going to worry about the histogram, Pearson's index of skewness, and outliers. Okay, so looking at page 322, we've got a survey of 18 high technology firms, and we've got a sample of 18 data spots. And so we've constructed a histogram here, divided into classes. You should have done histograms in your first couple units. And you can see here that this is pretty bell-shaped. It's unimodal. Okay. It's got a pretty good bell shape. There seems to be a little skewness here, perhaps. But is it enough to make it where we can't use the standard normal distribution? Well, we have to figure that out. And so you can construct a histogram and look at it. Now, I wanted to show you this. This is a picture of the calculator. And there's a lot of stats you can get in these 1-bar stats. And I made a video that I hope you can access when you get to this link. If not, I will try to post it. Actually, you may not be able to get to it. I'll try to post this video separately so you can actually see how it's done. But there's probably some things on YouTube that will show you. But the 1-bar stats that you can get, if you look here, this is your average, and this is for that particular set of data. Here's your X bar right here. Okay. This is your sigma squared, or XX squared. Here is your sample standard deviation right here. So we need this. We need this. If you look, this is our sample size. You keep scrolling down and this window shows, here's your minimum. Here's your quartiles. I assume you did box and whisker plots in the first couple of units. Here's Q1, your median, Q3, and your max. That's that 5-point summary. And your interquartile range, which you're going to need later, your IQR is Q3 minus Q1. And you're going to need that. That was the width of the box in your box and whisker plot. Okay? So let's go on. This is the screen, and the data, you can come back to this and see. But these are the numbers, and I got those using that set of data that was given and getting the 1-bar stats in the calculator. You know how to do it by hand. You may not know how to get it in the calculator. Okay, so we're going to go forward. Here's a check for skewness, and it's the Pearson's index for skewness, and this is the formula that you're going to use. So you need to remember this one. So it's 3 times the average or the mean minus the median. So that was 79.5 minus 77.5 over the sample standard deviation, which was 40.5. And we get a 0.148 right here. Okay. So 0.148 is not bad. What we want And what we're going to try to find, or what you're going to look for, is that the PI is not greater than 1 or less than -1. So it needs to be between -1 and 1. If it's between -1 and 1, it's good. We're good. Thumbs up. So it can be concluded that the distribution is not significantly skewed. And so that's what we're looking for, and that's where we are with this particular set of data. Then you're going to check for outliers. Now, an outlier is a number that is too far below our data, too far above our data. It's 1.5 times below Q1 or 1.5 times above Q3. And that's data that doesn't make sense. It's just too far out from all the other data. You know, maybe you were taking measurements in a lab and somebody bumped the scale. Maybe they just did something really stupid and measured something twice and didn't realize it. They added, you know, salt instead of sugar to the whatever. So it's a number that doesn't make sense because, you know, it just is too far out. And so we check to see if there's any outliers in our data. So, 5-number summary, remember I told you this is your minimum here. This is your Q1 here. This is your median. This is Q3. And this is your maximum. Okay, so this is your 5-number summary. This is your min. Okay, so what we're going to use is this IQR. Remember, the interquartile range is what that stands for. And the IQR is equal to Q3 minus Q1. So in this case, it's 98 minus 45, or 53. Okay, so that's your entire interquartile range. So I'll write that in here. It's 98 minus 45, which equals 53. Okay, so Q1 is 45 minus 1.5 times the interquartile range, and we get a negative 34.5. That's 1.5 times below Q1. Q3 plus 1.5 times the interquartile range gives us 177.5. There was no data in our data set that was below 34.5 or above 177.5. So we can say there were no outliers in the data. So we've done our 3 checks for to see if this will pass or be considered data that we could apply the normal distribution on. And we look, and here's our data set, and the histogram is approximately bell-shaped. The data are not significantly skewed. It fell within that -1 to 1 range. There were no outliers that were in, none of this data was above or below those numbers. So it can be concluded that the distribution is normally distributed, and then we can use these z-scores, we can use these properties in order to help us gain information from the data. So that ends 6.2, and we'll get this posted, and hopefully you can work on your homework. If you have any questions, be sure to be in touch and let me know.